Good morning or afternoon, evening even. This will be day number 6, I believe, of our electric fields or fields unit. We're working still on electric fields. And what we're going to look at today is potential difference. I think I'm going to do potential difference. I said last day that I was going to maybe do some practice ones, but potential difference is the last quantity or equation that we use in electric fields. And then that finishes up our electric fields area before we get into Kepler's laws and gravitational fields. Okay, so I thought what we'll do then instead is maybe I'll do that up and then maybe we'll split the hand, and instead of making one hand, and we'll do two small hand-ins, one right after electric fields and one right after gravitational fields. So that's what I'm going to do instead. Okay, so let's open our Blackboard up here. And what we want to look at today is we want to look at potential difference or electropotential difference. Voltage is kind of like the slang for it. And we're going to define what it is, what the equation is for it in current electricity. And then we're going to look at it in terms of an electric field and how it works in an electric field and how you get electropotential difference from point charges or charges in an electric field or two charges that produce fields on each other kind of idea. Okay, so we'll do that. Okay, so let's define first of all what we want to do today. I can't remember what day it is. I think it's day 5, but I'm going to look for sure here just to make sure. We just look back here. Give me a second. I gotta look it up here. Okay, so according to this, I gotta go all the way through that yet. Internet's a bit slow here. Okay, so Unit 3, electric fields. Yes, we're on day 6. We did day 5 yesterday. So this will be day 6. Okay, so day 6, Unit 3. This finishes up all our work on electric fields, probably, if we get done today. And what we're going to do today is we're going to look at potential difference. Okay. Basically, we're going to define it first. Okay. And then we're going to look at what the equation for potential difference is, which is sometimes called voltage. And then we're going to look at potential differences in electric fields. And that's probably what we're going to do a couple examples of those. There's a couple equations in there. One of them, we used to do current electricity in physics until they changed the curriculum 2 years ago, but now we just do fields. And then you can probably see current electricity in like PAA or in grade 9 science or 8. I can't remember which one it is as well. So let's get into what we're going to talk about in terms of electropotential difference. So electropotential difference, or voltage as it's mostly called, is basically when you do some work or use some energy on a charge to move the charge through a field against an electric field, which is a force, right? Which is creating forces, or pulling it out of an electric field. So that's kind of what it is. So let's start by defining that first. So we call it potential difference. Slang for that is voltage, because that's the unit. It's used, volts are used to measure it, so people call it voltage, but it's really called, the technical term or the proper term is potential difference. But potential difference or voltage is basically, this is the work done or energy, because remember that energy needed. Okay, that energy and work have this equivalent units. It's the work done or energy needed to move a charge in an electric field. Oops. And if you think about voltage, voltage is always between 2 points, okay? Right? The reference points that you're looking at. So if we're looking at potential voltage equation, okay, a voltage or a change in voltage is equal to, let's use the skinny marker, it looks better. Okay, a change in voltage or potential difference is equal to the work done, can also equal energy, over the charge. So it's a real simple equation. Okay, so this is potential difference, change. Okay, we'll put change on top. Sometimes it just uses a V there, some books, so that's okay. And it's measured in volts. Okay, this is the work done or energy, if you like, because they're equivalent units, and that's measured in joules. Okay, and this is the amount of the charge that you're moving through the electric field. Okay, charge amount, and that's in coulombs. Okay, so if we look at it, 1 volt is equal to 1 joule per coulomb. Okay, that's the potential difference. Okay, if you look at the equation. Okay, so that's a basic equation. Often you'll see that equation written in this form. Work done equals change in voltage times Q. Okay, often it's written like that instead of in this particular way, but they're both the same equation, just one's written as a fraction and the other's written as a multiplying statement. Okay, so when you have two charges that are of opposite charge, you have a force of attraction there. And basically, potential difference is the amount of work that you have to do to move that charge within a field. So you have to think of it that way. So let's look at the two simplest situations you can have. Okay, let's say that we have two charges. This is one charge here. Say it's positive, and one charge here is negative. Okay, so that in between these we have a force of attraction. Okay, so this positive charge is attracted by a force towards the negative one, and the negative charge is attracted by a force towards the positive one. So they're going to want to come together like that. So we have a force of attraction in there. Okay, so if we want to move the force away from them, okay, if we want to take this charge and we want to pull it apart, if we move the charge farther, okay, right, we're gonna gain some electric potential difference. Okay, gain some electric potential to want to move back into each other. Okay, we're working against the force of the electric field. Okay, so if we're going to move it away, either this one or this one, if we move it away, let's maybe use a different color there. So that's representing movement. So we're moving it against the opposite direction of the force. Let's get rid of that thing. It's in my way there. Oops. What the heck? Not that one. No. Not that one. There we go. Sorry, I just had to get rid of that. Okay, so we're moving it away. We're going to gain some electric potential difference. Okay, so we gain potential difference Oh, yeah, no worries. Okay, I must have made an error there. Let me fix that up. So that's the day 21. Okay, so yeah, I probably put it in the wrong spot like I did last time. I will do that and get that fixed in the next 15 minutes here. Okay, thanks, Colin. Bye. Okay, I got to go fix a problem here, so I'm just going to pause you guys for a sec. Okay, sorry about that, guys. So we're gaining some potential difference if we're pulling them apart. Let's get that a little note. Gain some potential difference. Okay, because we're pulling them apart, so we're going opposite of what the force is. So we're pulling them apart. Okay, the opposite. If we have two opposite, the opposite is true. If we push them together, we're losing potential difference because we're helping them get together. We're not working against the force. Okay, if we do the opposite diagram, if we have two unlike charges, okay, we have a force of repulsion here. So in the middle here, we have like they're not going to be pulling towards each other. So this one's going to be pushing on this one, and this one's going to be pushing on this one. So we have a force of repulsion. So in order to gain electric potential difference, we have to move this one here. So what's going to happen is, think of it as if you move it there and you let it go, it's going to shoot it back out. If you move it out here and you let it go, it's going to shoot it back in, right? So we have to move it. We'll use the same color here. So we have to move it in closer together. So if we move the charge in, charge is closer, we'll say. we gain electric potential difference. Okay, so if we can summarize that, you're basically gaining electric potential difference. You're working against the force, or you're working in against the force, and you're doing work to move that charge. If it doesn't take any energy to move the charge, you're not gaining electric potential difference. So you have to do work, use energy against the force, against the electric force, to increase your electric potential. Oh, damn. So in our cases, we had, if you push too, so that would be to gain that, pushing two like charges closer together. Whoops. This is supposed to be both positive here, guys. I did the same. I did a positive, negative on both of them, right? This one's supposed to be positive, positive, right? Two like charges closer together, right? Not two. We did two different ones already, right? Okay. Hopefully, this one's two opposite charges. You can pull them apart to gain electric potential. Two like charges, you push them together to gain electric potential. So in order to gain the electric potential energy, pushing two like charges closer together. Okay. The other one that we did is pulling apart two unlike charges. And so you can interchange voltage and electric potential as much as you want. Some physics teachers want you just to use electric potential because that's the technical term, but you can use voltage, and I'll know what you're talking about, and I'm fine with that, as most electricians do that. Okay, so if you have a uniform electric field, you can get a voltage with a particular formula. So if you remember, um, the electric field formula that we just did the other day, and if you remember the formula that I just did on top for work, we can calculate basically a pretty easy equation for finding potential difference in an electric field. Okay, so let's do that on our next page here. So Potential difference in an electric in a constant electric field or a uniform electric field. Okay, so we have a few equations that we need to work with. Okay, we know that potential difference. I want to get this skinnier. Potential difference, or V, change in V, it's equal to work done over charge. Okay, and we know that the electric field formula is force over Q. And we know that work from last unit is force times distance that you move something. Okay, so if we take this equation, plug it in there, rearrange this one for Q. Okay, Q, EQ equals force. So then if we divide by EQ equals, Q equals force over electric field. Okay, if we plug this one into there and this one into there, we can get another equation for a uniform electric field. So let's do that. So let's go ahead and put work, which is FD. So let's say force times distance moved. Okay, plug that in. Let's plug this one in for Q. Q is F over E. Okay, now you're like, okay, well, that's kind of all weird. Well, we can easily cancel out the F's, but we have 1 over E. So remember, we have to take the reciprocal and multiply when we're dividing by a fraction. So we're going to multiply by the reciprocal of this because this is a fraction, and the F's will cancel out. So we get, as our final equation, a voltage in a uniform electric field equals the electric field times the distance that the charge is moved. And there is a simple equation for potential difference in an electric field. This is our potential difference. Okay, this is our electric field. And this is the distance that the charge is moved in the electric field. Sorry. Okay. Okay, so the distance that you move in the electric field, or how far apart two charges are, or something like that. How much you move. Okay, so how much did you pull that? How much did you pull that charge? So if you had two opposite charges together like this, and you wanted to get the potential difference, how much did you pull them apart? That would be that distance and then that you would need. Okay, so we'll take a look at those. Now, what are the units that are involved in here? Well, we have volts here. Electric field is obviously calculated as newtons per coulomb. and distances in meters. So you're like, whoa, that's all weird. How do they actually equal each other? Well, if you look at it, newtons and volts are not base units, and neither is a coulomb. Okay, so you're going to end up getting a voltage. If you remember, if we go back to the beginning page here, a volt is the same thing as 1 joule per coulomb, right? So this is a joule per coulomb here. So somehow we have to change a Newton meter is the same thing as a joule, right? Okay, so let's take a look at the units. So if we say a volt, so if we do the formula, a volt is one joule. What the heck am I doing? Newton here. Sorry, guys. Having a brain block here. 1 joule per coulomb. That's what brain blocks happen on Friday. Joule per coulomb, right? Okay. And that's going to equal electric field is a Newton per coulomb times a meter. And remember that a Newton meter is the same thing as a joule. So they have 1 joule per coulomb equals 1 joule per coulomb. So we have equivalent units, so it makes sense. Okay, so this is the big formula that we're going to do a couple examples of here. Okay, so looking at our plan for today. Okay, so we've defined what electric potential difference is. We looked at the voltage equation in this form, and we also looked at the potential difference of in electric field. So all we have to do is do a few examples of this, and then we're done for electric potential difference. So let's do that. Okay, so oops, let's not go too far back here. So let's start off with a real simple example calculation that you might commonly see in this area. Okay, so let's say that you have 2 charged plates. Okay, let's do a picture of it. Okay, so I'm going to draw, they usually 2 charged plates, okay? So let's say that they're like this. And then let's say that on the bottom here, we have the negative plate. Okay, and on the top here, we have the positive plate. So we're going to have an electric field that creates a force of going downwards. It's going to go from positive to negative. Okay, so let's draw some little arrows in there. I think we just got one of those. We can just do. So it's going to go down like this. This is going to be our electric field. These are going to be lines of force. Okay, and it'll be straight like this because these are 2 flat plates. They're not point charges. Okay. And let's say that there's an electron in here, which is negative charge. It's a negative charge. So the electron charge, 1 electron is 1.602 times 10 to the negative 19 coulombs. Okay, that's called the elementary charge on an electron. Okay, and let's say that the distance between these two, let's say it's 0.22. That's too far apart. That's not going to give us very strong. Let's put an extra 0 in there. Let's say that those charged plates are 0.022. So 2.2 centimeters apart. Meters apart. Okay, so we have that, and let's say that the electric field strength between these, let's see, this field here is equal to 7,500 newtons per coulomb. Okay, so we have an electric field strength. We have how far apart the plates are. We have this electron floating in there in between these two plates. Okay, so our question is, given all that, okay, A, what is the voltage difference or voltage between the two plates? Question mark. And B, how much work or energy, if you like, is required to move the electron towards the negative plate. Okay. You're like, well, don't you have to know the distance if you're going to move it? Well, not necessarily, because you're going to end up using the work equation. So, okay, the distance between the two plates. So we want to find what is the voltage between the two plates. So we can use the equation that we had up here, E times D. Really quite simple to do. Okay, so the electric field that we had was 7,500 newtons per coulomb times our distance of 0.022 meters. Okay, a Newton meter, that's going to give us so many volts, right? So if we multiply those two together and round off to two significant figures, well, let's see what we get. 7,500 times 0.022, 165 volts. Okay, if we did two significant figures, that'd be 170. Okay, then the question is how much work is required to move the electron towards a negative plate from here to there. Well, work, if you remember, change in V equals W over Q. That was our first one that we looked at. If we want work, that's going to be change in V times Q. And Q is the size of the electron, which I gave you the elementary charge of an electron. A lot of times they use electrons or protons for their charges in these questions. So the work done is going to be 165. I'm not going to round it off or use the rounded off one till the end, and times 1.6 times, I'm only going to use two significant figures. I know that's got O2 there, but we only need two significant figures in that one, times 10 to the negative 19 coulombs. So if you multiply those two together, you get 2.6 times 10 to the negative 17 joules of energy to move that electron. So fairly simple using those two equations. A lot of times they'll give you two electric plates like that are some distance apart. Okay, let's do one that has some words in it. We'll do one more example of this. Okay, and then we'll call it a day, I think. What do we got for time here? Yeah, we're at 34, so we'll stop around 40 minutes again. Okay, if you want to try it yourself, you can go ahead. A charge with a magnitude of, let's say, 1.8 microcoulombs. Is in an electric field with a strength of 4,600 newtons coulomb. Okay, find the distance the plates are apart. Okay, if the voltage between them is, let's say, I don't know, let's say it's a 1,500 newtons or volts. Say it's a really high volt. Well, let's not go that high. Yeah, what the heck, we can go that high. 1,500 volts. Really charged up. We got a bigger force than an electron in there. Okay, and B, how much work is done? It's needed, we'll say, to move the charge to the positive plate. Okay, because we have positive charge, so we're moving it again towards that, so we're getting some potential difference. Okay, you can try that yourself if you want to pause and do that. If not, I'm going to work it out here. Okay, so this one here, same as we did before. This time we have a change in voltage is equal to the electric field times the distance. In this case, we are looking for the distance. So the distance is going to equal the change in volts divided by the electric field. Okay, so 1,500 volts divided by 4,600 newtons per coulomb, and that's going to give us a distance. Okay, so if we do that one, we get 0.326 or 0.33 meters or 33 centimeters. Okay, in this case, how much work is done? Okay, so if we remember, change in voltage equals work over charge. So if we rearrange that into work is equal to change in voltage times charge. So that's going to be our voltage of 1,500 volts times our charge value of 1.8 microcoulombs. So that's times 10 to the negative 6 coulombs. Okay, and you end up getting 0.0027, or if you like, 2.7 times 10 to the negative 3 joules. Okay, so that's a typical voltage type problems that we have. Okay, so that kind of brings us to the end of the fields, electric fields area that we need to study, looking at all the areas in that are in the curriculum for that. Okay, so what we'll probably do here is maybe tomorrow we'll uh, talk about Milken's experiment for a little bit, and then we'll, like I said, I'm going to split the hand-in into two pieces. I'll do a really short 5 or 6 question hand-in for electric fields, and then we'll start gravitational fields after that. So that's where we'll stop today. Probably open up that hand-in for you tomorrow, and you can probably get it done in less than a period anyway. Okay, so good luck.